So let me just say this again. These were two homework problems you're asked to look at. The question was, are the points A, B, and C collinear, and the points D, E, and F collinear? And it's sort of tough to talk about this because we haven't even talked about what lines in 3D, right, look like. But yesterday, we did a little bit of work to arrive at what I called the vector form, or the vector form or equation of a line in 2D. So just a quick recap. We started with, we have a line y equals 2x here. Here it is, y equals 2x. And we looked at how to take that into something like that would look like a parametric equation. So we've seen parametric equations before where you have, x equals some function of t and y equals some function of t. We discussed briefly, I think it was Reed or someone who told us, hey, look, this would just give us a line segment, right? I forget who said that yesterday, but if you're going to block off t from 0 to 4. And then I introduced you to this idea, right? So I'm saying R of t is typically how we're going to name our functions, our vector functions, is usually what they called. R of 0 is a starting point. This is where our line starts. It could be any point on the line. And then I introduced you to the idea of a direction vector, which some of you felt comfortable with, some of you didn't, or maybe you didn't know it before. But basically in a direction vector, your A value is delta x and your B value is delta y. And we multiply that by some scalar t. So again, we would need to specify a domain for t. If we want to get the whole line, then we would just say t is an element of the set (-infinity to infinity). Okay. The reason I went to all this trouble to get the vector form of a line in 2D is because this is the exact way we write a line in a 3D world. Okay? So that's what we're going to do. I guess we'll take these points A, B, C, D, and we'll work with those first. So here, let's go to a new page. Our goal is to figure out if these points are all on the same line. Bless you. Okay. So my plan is going to be this. Okay, we're going to find an equation for a line that contains, I should say contains, or passes through maybe, points A and B. And then once we do that, we'll check if C is also on the same line. Okay? So this will be the part. The second part will be, well, how do we do that? That'll be a little bit different than what you're used to. Okay. First things first, we're going to find the equation for the line that passes through points A and B. Okay? So I am not going to attempt to make this picture perfect. What I am going to say is this. Just pretend for a minute. Here's point A floating in space somewhere. The point 2, 4, 2. And somewhere else in space is the point B, which is 3, 7, -2. Okay? And my claim is we actually know how to give instructions to get from A to B. And I say give instructions because that's what I want you to think of like direction vectors like. They sort of tell you how to head, which direction to head in, and how to move in each of the components. So for example, we can move to get from A to B. We just give this a little bit of thought. We can figure this out, right? I'll just call this new vector, I'll call it D, vector D for direction. Let's think about that. What change in x would we need to get us from the x-coordinate of A to the x-coordinate of B? Good. We just need 1. We need to go up 1, right? That would do it. Okay? And let's think again. What change in y will we need to have to get us from the x-coordinate of A, I'm sorry, not the x-coordinate, but the y-coordinate of A to the y-coordinate of B? We've got to vote for 3. And I don't see any objections, which is good. Okay? And then lastly, we want to get from the z-coordinate of A to the z-coordinate of B what delta z are we experiencing? -4. Okay? So this is the direction vector of our line. It's saying if you want a line to go through points A and B, it needs to head in this direction. Okay? There's one small thing we have to be careful of, though. There are many lines that head in this direction. Right? We could pick any point in 3 space and head in the direction of this vector, and we'd have a line that would go in this direction. And as a matter of fact, all those lines would be parallel. It's sort of fun to think about what parallel lines look like in 3D world, right? Because you could have a whole family of them all pointing in the same direction. Okay, so what's next? Well, I'd like to make sure that it goes through one of the points I have. So I'm going to choose point A as my R0, my starting point. Okay, so we're going to write our line now. It's going to be R of t equals 0.242. Okay, which, by the way, if in your textbook, when you see 242 in parentheses like that, we think of that like a coordinate, right? Your textbook sometimes calls this a position vector. Gives new name to the coordinate 242. The reason it's saying this, so the special thing about a position vector, is that its tail is at 0, 0, 0. So you should just make a note of that. My board's calculated. Tail at 0, 0, 0. Okay? That's what makes it a position vector. Okay? If you see the notation like we see up here, like the direction vector has this new different vector notation here. It doesn't look like a coordinate. That just means it's a set of delta x, delta y, delta z that can start anywhere. It just gives us a direction. All right? So to finish the equation of this line, we do plus some scalar t multiplied by the direction vector. Okay? And you can sort of check right now that it goes through the points A and B that you want it to go through. So I'll ask you guys, what do you think t should equal? In other words, what do I want to multiply this direction vector by so I get back point A? I think 0, right? Point A is, let's just not lose track, point A is 242, right? I don't want to change it at all. I don't want to change it by 1, 3, and -4. I want it to stay at 242. If I want to stay at 242, then t should be 0. So this corresponds to t equals 0. Now, I'll ask you this question. How many times do we need to add the direction vector to the point A to land on the point B? And I'm being very careful with my language here. I'm saying, how many times do I need to add this vector? Just once will do it. So I'm going to let t equal 1. Now you can check that. If I multiply, if this is t equals 1 here, then these numbers come back exactly the same. And if I add them, 2 plus 1 right here, this 2 plus this 1 gives you 3. This 4 plus this 3 gives you the 7, right? And then this 2 plus this -4 gives you the -2. Okay? That's it. So this line goes through the 2 points we want it to go through. Now, the magic question, well, not a magic question, but whatever. The question we're interested in, does this same line eventually land on this position vector, or this point 1, 3, 3? Okay? So what I'm really saying is, does 1, 3, 3 equals 2, 4, 2 plus t times the direction vector we had before, which is 1, 3, -4, have a solution? Okay? So if that has a solution, we're set. Right? If there's some t we can plug in here, right in there, and make this work, we're going to be happy. So I'll make a claim. I make claims a lot. I claim that there's 3 little tiny equations hiding in here. Right? Jerry? Right? 1 equals 2 plus t. Right. And that t is coming from t times 1. So this is what it means. I want these x coordinates to work out. Right? 3 equals 4 plus 3t. That comes from these components having to be equal. Right? Yeah. So then lastly, that's right. So let's use a different color here. I want the z components to all equal each other. Right? So what do I get here? I get 3 equals 2 plus negative 4t. All right. So you're stuck with this system of equations. It's not like a system in the sense where you got to find more than the value of more than one variable, but I do need this. I need the following to happen. I need the same value of t to make all these equations true. I need to make sure that at some point in time, though, that this equation of the line here, which you could temporarily think of like this, right? That all these guys will give me all of those guys for the same value of t. All right, so it's up to you how you want to start. We could simply do this. We could take the first equation, right, and solve for t. So if we take that first equation, that tells us t has to equal negative 1. That's the only way that first equation is going to be satisfied. So now we've got to hope that t equals negative 1 works in the other equations. Well, let's try the second equation. So we take t equals negative 1 and plug it into equation 2. That would imply that 3 would have to equal 4 plus 3 times negative 1. But that doesn't happen. So that means that these points are not collinear. There is no value of t that's going to make all these equations satisfied simultaneously.